Right, in this video, we're going to introduce the idea of correlation between two variables that we're measuring for the same individuals. So Chifaru, she's a big math nerd, right? So she's going to track her weight. She's Australian, so it's going to be mass in kilograms over the last 20 months. And she's also going to record the number of times per month she worked out. So this is two different data sets over the same months. Right? So here are her data. Right? She worked out 4 days one month and her mass was 33.1. She worked out 11 days a month, her mass was 30.9 kilograms, etc. 23 days a month, mass was 24.8 kilograms. Right? And what she wants to know, if there's any association between these two data sets, between her weight and how often she works out. Now, the logical first step is to graph them and see if any pattern appears. Because if there's any pattern, then there's probably some idea that there's an association between the two. One might cause the other, or the two might be affected by an external factor. And this will tell us if there's some kind of association. All right, so here's our graph, weight in kilograms versus days worked out. We put days worked out on the x-axis, the weight in kilograms on the y-axis, and the dots represent each month, right? So in this month, she had a mass of about 35 kilograms and worked out about 6 times, maybe 5 times, right? Somewhere in here. Right here, her mass was about 20 kilograms and she worked out, looks like about 18 times in that month, okay? So the position of the dots tells us where it is in each of the two variables. Each dot represents an individual. In this case, it's going to be a month. Historically, on the x-axis, this is usually called the explanatory variable, and the y-axis is sometimes called the response variable. But that language is more suggestive than anything, right? Sometimes one doesn't cause the other. Sometimes they're caused by an external factor. But if we just look at the pattern, right, it looks like there's some association here, right? As the number of days we work out per month goes up, our weight seems to go down. Okay? So there seems to be an association, right? The more days worked out, the lower the weight, right? We will call this a negative association, right? Because as one increases, the other decreases. If they both increased, it would be a positive association. But we also see that it's not on a perfectly straight line. There's some cloudiness to the data, right? So in correlation, we're going to measure how good this association is, or how closely the data follows a straight line on our scatter plot. Right? The big thing that we're going to measure is what's called a correlation coefficient. This is given the number R. R is a number between -1 and 1. And if the scatter plot is on a straight line, the correlation coefficient is either 1 for a perfect positive linear association, as one increases, the other increases, or -1, it's called perfect negative linear, right? If one of them increases, the other one decreases. And the more cloudy the data gets, right, the more scattered it gets, the closer the correlation coefficient gets to 0, right? 0 is in the center. 0 means that there doesn't seem to be any relationship between our data. Next, we're going to take a look at some examples. If R equals 1, we have a perfect linear relationship, right? It's a positive linear correlation, right? Our correlation coefficient can only tell us whether or not it follows a perfectly straight line. There are certainly some other shapes that would show some kind of correlation, but R does not tell us anything about these. Okay, so we don't want to use R if we have a curved shape. It only tells us the linear. So 1 is perfect positive linear. If we have an R of 0.9, we certainly have a really strong positive linear correlation, right? As one of them increases, the other one also increases, but it might not be perfect. There's some scatter, there's some cloudiness to the data. And as our correlation coefficient gets closer to 0, right, at 0.7, right, we can still see a trend, but there's all of a sudden an awful lot of mess in our data. Once we get to 0.5, it's getting tougher and tougher to see the pattern. Right? I had a tough time getting a piece of data with an R of exactly 0, so if I have a negative 0.009, there doesn't seem to be much of a pattern here at all, right? It's just a giant mess. So no noticeable correlation. They aren't affected together. One doesn't affect each other, and they certainly don't seem to be affected by anything external. If an R of negative 0.51, the negative means that we have a negative slope, right? This would be a negative 0.51 is a moderate negative linear correlation. It looks like as one of them increases, the other one's decreasing, but there's certainly some scatter to the data. R of negative 0.74, we have a little more of an impact. We certainly see a nicer pattern as one increases, the other decreases. And then if we have R of negative 0.98, we have a very strong negative linear correlation. They're following a really nice straight line. There's, of course, some variance, but in the real world, there's almost always variance. All right, so let's go back and look at Chief-Aru's weight versus days worked out. Right? We definitely have a more negative pattern, so our correlation coefficient is expected to be negative. It's a noticeable pattern, so we would expect R to be maybe 0.7, 0.8. It's going to be negative because it's going down. Right? A negative correlation. As the days go up, the weight's going down. Looking at an actual number, the correlation coefficient for this data is negative 0.705. So this we would call a moderately strong negative linear correlation. But the statement we want to make doesn't use those words, right? What we just say is as the number of days worked out per month increases, Chief-Aru's weight tends to decline, right? These scatter plots, this correlation coefficient, they'll just talk about the tendency. They won't say exactly, right? So if we go from here, we could go up or we could go down, but the general gist, we would expect it to go down more often than it goes up. But the real world data isn't perfect, so we wouldn't expect this to be either.